you want to do a little the housekeeping, Lori, or?
Oh, I already did that.
Okay. And I'm going to give a little shout out. Saturday, 9 to 12 here at the office in the parking lot is shredding day. So bring any of your things you would like to shred. Mostly paper type products. They are not going to be doing CDs this year, but paper clips and staples are okay. Okay. Good morning, good afternoon, everyone. Welcome to our Lunch and Learn series. Today, we're going to be listening to Bill Welsh, who's from the Hamden North Haven Village, about NASA's Project Dragonfly. I have to admit, I've been looking forward to this for quite some time. Bill is an engineering graduate of SUNY Buffalo and Cornell, and he has been an engineer at Sikorsky for many years and is assisting the Johns Hopkins Applied Physics Lab, who is the prime contractor for the Dragonfly mission. And I'm going to let Bill take it away so that he can explain what this is much better than I am. Thank you, Bill.
Yeah, thank you, Kate. Thanks for the introduction. Yeah, Bill Welsh here. I've been with Sikorsky for 43 years. After graduating from Cornell with my master's degree. It's a super place to work. You'll see it if you travel on the Merritt Parkway over the Sikorsky Bridge and look to your right. You'll see a big factory, and that's where I am right now. I'm in my office. It's an amazing place. Titanium and aluminum come in one side of the factory and helicopters fly out the other side. I'll show you some of the helicopters we make. But what I'm going to be talking about today is an unusual helicopter, you might call it a drone, that's going to take off from Cape Canaveral in a couple of years and fly to a moon of Saturn called Titan. And I'll show you some details of Titan and how it's an unusual place. The program is a NASA program, like Kate said, being run by the Applied Physics Lab, which is part of Johns Hopkins University in Maryland. You might have heard of the Jet Propulsion Laboratory on the West Coast. This is like an East Coast equivalent to that, not JPL, but APL, Applied Physics Lab. You see this first chart here was put together by Elizabeth Turtle, who is the Dragonfly principal investigator. In other words, she's leading the whole program, has an unusual nickname called Zibby. So Zibby Turtle is our leader. You see the people in the tiny inset on the bottom right. Those are the folks at APL that are working on this project in Maryland. So I'm going to be showing you the details of the actual vehicle that's going to be sent to Titan, and also the mission itself. How do we get to Titan? And also, of course, why we're going to Titan. I'm also going to give you some background about Sikorsky very briefly. But first, here's some background about my family. That's me on the left, holding my grandson, showing him some of the principles of vertical flight. He's a lot bigger than that now, and I can't do that anymore because he's almost as tall as I am, if not taller. You see on the middle bottom, that's my lovely wife, Bernadette. We've been married for 50 years. In the upper right, you see my daughter and my son, my younger son, Jeremy, my daughter, Gail. And on the lower right, my son and I, Bill, my oldest son, Billy, our oldest son, we're out fishing in Maine. So that's my family. So here's some of the products that Sikorsky makes. The 76D is a civil helicopter. The S-92 is a civil helicopter. And if you Google the president rides a new helicopter, you'll see that we're making a helicopter like the S-92 for the president of the United States. As a matter of fact, he did his first flight a few weeks ago. So I think you'll be able to find that online if you're interested. That's going to replace a 1960s vintage helicopter as Marine One. They call it Marine One instead of Air Force One because the Marines fly the president. So we make the 53K, which is a huge heavy lift one. If you do look down on our factory, sometimes you'll see one of these out on the flight field. And on the production line, they're they're making these as fast as they can. And then the Black Hawk, the UH-60M is a Black Hawk, and so on. We also make experimental aircraft and flight test them down in our Florida flight facility. I have some videos here, but I'm afraid they won't play over the Zoom, so I'm going to skip them. But when we finally get this on YouTube, you'll be able to watch those. So before I get into the Dragonfly project, I'm going to show you some of the principles of helicopters that I deal with a lot, since I'm a dynamics person. In other words, I work on vibration and stability at Sikorsky. That's my specialty. That's what I've been doing for 43 years here. So this is a picture of a helicopter rotor in hover. And you see the dark arrows here. I think you can probably see my cursor. These dark arrows represent the wind velocity when the helicopter is just sitting in the air hovering. It's not going forward. In that circumstance, there's no vibration coming from the rotor, and the helicopter is very, very smooth, like an airplane, except it's sitting in space above the ground, not moving forward or aft or sideways. All those little vectors represent the airspeed, and you can see it's on the order of 670 feet per second. So very high airspeed at the tip of the main rotors. All American helicopters turn counterclockwise while looking from the top down. And that's what this picture shows. This rotor is going around counterclockwise, and you get this high velocity at the tip. But when the helicopter starts going forward, something changes. You get an asymmetrical velocity over the rotor. You get a very, very big velocity on the right-hand side of the rotor and a very small velocity on the left-hand side of the rotor as you fly forward. Your forward is up in this picture. So you can see that on the right side, you get 870 feet per second, and on the left side, you get 470 feet per second. That asymmetry is what causes vibration in helicopters. So if you've ever been to Hawaii or the Grand Canyon and riding a helicopter, you'll notice that it shakes. And it shakes because of this asymmetry. On Dragonfly, our job is to make sure that the shaking doesn't damage the equipment on the scientific instruments and the navigational equipment on Dragonfly so that it doesn't crash. And so it can do the science it's intended to do. So this is the result you get on a helicopter flying forward. You see the lift distribution is very high on the right-hand side and very low on the left-hand side. Again, that's what causes vibration. Another thing dynamics guys do is they work on stability. This is a picture of a glider being flown so quickly that it's the wings actually go unstable. I think you'll be able to see it. If you probably can't hear it, you can see it. You see how the wing is fluttering like that? That fluttering is like a flag fluttering when the wind blows on it. The pilot did that on purpose in order to determine what the flutter speed is. Then when they sell this glider to people, they say, don't go to that speed because that's dangerous to do that. So at Sikorsky, I work on making sure that our vehicles don't have any flutter issues because it's dangerous and it can cause a catastrophic accident. We also have other kinds of stability problems caused by interaction between the rotor and the fuselage. This is an example of that. And again, you won't be able to hear the noise perhaps, but you can see that this is a bad event. This is a Boeing helicopter being tested on the ground, and you can see it wagging kind of side to side. And it gets worse and worse and worse until parts start to break. So this is a really bad day for the test engineers. Yeah, not a good outcome. So the group that I work in and my job is to make sure that doesn't happen on our helicopters and that it doesn't happen on Dragonfly. And we know the methods to do that. So how did Sikorsky get involved in this project? Well, it was a little bit of a circuitous route. We make helicopters for the president, for industry, for offshore oil rigs, for the military, but we don't typically do NASA projects. So I kind of plotted out how we got involved in it. Sorry for all the words, but I'll lead you through it. So the Applied Physics Lab won this contract from NASA, but they don't know how to make helicopters. They make satellites, and they've made a lot of satellites, and they're very good at it. But they don't make helicopters. They don't know anything about aerodynamics because they're in space where it's a vacuum. So they contacted Penn State. Well, why did they contact Penn State? Because there are 3 centers of excellence for vertical flight in the United States. The Army actually funds these 3 centers of excellence to develop new techniques and new technology for all of the helicopters in the country. Penn State, University of Maryland is another one, and Georgia Tech is a third. Well, they contacted Ed Smith at Penn State, and Ed started to have his PhD students work on the project. But then APL, after starting it and getting a lot of good work out of Penn State, the cadence wasn't high enough for the program. The Penn State students would graduate, they'd have to start over again with a new PhD student. So it became really hard to use a university to analyze all the things they needed analyzed, for example, dynamics and aerodynamics. So Ed Smith knows me, and I know him, of course. He contacted us, APL contacted us, and we got involved. So currently there's about 10 engineers working in dynamics, aerodynamics, ground testing, and rotor design. So here's the vehicle that's going to go to Titan. It's about the size of a Mini Cooper, and it's the vehicle on the right here. It's the size of a Mini Cooper, and it weighs about 2,000 pounds on Earth. For reasons that I think you'll understand later, it weighs a lot less on Titan. On Earth, it weighs 2,000 pounds. On Titan, it weighs 200 pounds. So 10 times less, almost 10 times less, not quite, maybe 250. And you can, some of these words here tell you what equipment is going to be on Dragonfly. There are many cameras, right here, forward cameras. There's actually a radar called a LiDAR on the bottom of the vehicle also. There's 8 rotors. You can see one rotor is right here, and another rotor is right below it, right here. And this rotor spins in the opposite direction from this rotor. So they're coaxial rotors, but they spin in different directions. And if you count, you can't see the ones in the back here, but there are 8 rotors total. There's a drill here on one of the landing skids right here. There's wind sensors. It's actually powered by a thermoelectric generator that uses plutonium to generate heat. And the heat generates electricity when you expose dissimilar wires to that heat. So we have that thermoelectric generator called an MMRTG power source. That generates the electricity, which charges batteries. And it charges the batteries for about a month. It takes a long time to charge the batteries. And then it flies once a Titan day. Once a Titan day, which is every every 16 Earth days. So it has antennas. It has a low gain antenna, which doesn't have a very high data rate. So you can't send much data back on the low gain antenna, but it has this big dish it's shown here, and it's on the ground position, and that points directly at Earth. And so all the scientific data that's collected can go through that high gain antenna to one of those big dishes on Earth that you sometimes see. That's what collects the data from the signal that comes from this. Has to be a huge antenna, and NASA has those. And so the data is downloaded and scientists can look at it. The vehicle actually travels to Titan in a shell structure, as you can see over here on the left. You can kind of see the lander in this phantom view here. It travels all the way to Titan in this vehicle, and then parachutes deploy, and it lands on Titan. So this picture is amazing to me. It shows the actual route to Titan. And it's important to notice that the Earth orbit is shown as a dotted line here. So over here on the left, right, where is it? It's right here. Oh yeah, right here. So you launch right here. Of course, it's on the dotted line because you're in Earth orbit, you're on the Earth. And look how many times it goes around Earth and even goes close to Venus. You can see it goes around once, then twice. It gets close to this outer dotted, or sorry, the inner dotted line, which is Venus's orbit. And then eventually it shoots out past the orbit of Mars, past the orbit of Jupiter, out to Saturn, the orbit of Saturn. And that's when it lands on Titan. So why does it loop around so many times? Well, it's using gravity assist. In other words, it gets launched from Cape Canaveral, but it doesn't have enough velocity to get out to Titan. So what the scientists have figured out is if they orbit near Earth and near Venus, they can have those planets actually pull the vehicle and make it go faster. So as you spin around Venus and Earth this many times, the vehicle is getting faster and faster until it can escape the inner solar system and shoot out to Titan. You can see these symbols here, VGA, EGA. EGA means Earth gravity assist. VGA means Venus gravity assist. So it's getting assisted from Earth twice and from Venus once to speed it up. And then when it gets to Titan, it doesn't orbit around Titan at all because there's not enough fuel to stop it. It's going so fast that the only way it can stop is by plunging into the atmosphere of Titan and using friction and aerodynamic drag to slow the vehicle down. So you can imagine this is a very precise aiming problem. And on the way to Titan, there's rocket fuel in that capsule to cause it to just slightly adjust its orbit or its trajectory so that when it finally gets to Titan, it can hit exactly where they want to hit Titan, because they have a place on Titan that they want to land. It's not arbitrary where you land. They want to land in a precise location. So some more details of the vehicle. Cameras on the bottom, imagers. Here's the LiDARs. These are the radars, navigation cameras, and the forward science cameras. Now, one of my jobs here is to make the vibration of the vehicle less and less, not because there are people on it. There are no people on this vehicle. Nobody's going to go to Titan. This is a drone that's going to fly autonomously all by itself on Titan. So the way it's going to navigate around Titan is by using the cameras. So you can imagine what happens if a camera is shaking, and you know this from probably your own experience. If you take your camera and shake it and look at the picture that results from that, it's blurry. So having a blurry image when the scientists look at the cameras will make the cameras useless. What they want to see is how big is the dune or the rock that I'm going to land on. And they want to avoid obstacles like that. And there are some obstacles like that on Titan. So one point to looking at vibration and minimizing it is to reduce jitter. That's called jitter, that blurring effect. Reduce jitter on the cameras. The other reason to reduce vibration is because equipment fails if you shake it. So this vehicle is just absolutely stuffed with scientific instruments and with flight control computers, things that actually control the flight. So you can imagine if you shake that equipment too much, you can fail it and either crash because you failed something critical to flight or destroy the science mission. So that's really our prime objective in my group, is to reduce vibration so that we don't fail equipment and we don't blur the cameras. So I already talked about the multi-mission radioisotope thermoelectric generator. That's a mouthful, MMRTG. There's the direct-to-earth communication with the dish. And then, of course, there's aerial imaging. That means imaging when you're flying and then imaging when you're on the ground. to plot out your course and to just to see what the terrain looks like. So why are we going to go to Titan? It's a big, expensive mission. It's a $3 billion mission. Thank you very much for paying your taxes, because that's where the money comes from. But why go to Titan? It's way far away. Well, it's because scientists want to understand how how life started on Earth. And Titan is one of the places in the solar system that is very much like Earth, the early Earth, before life arose. So that's the paradigm that NASA follows. Where in the solar system can we find hints about how Earth developed and how did life on Earth arise? So Titan is similar to Earth because it has liquid water. That's one of the big important elements. Also, it has a lot of hydrocarbons, a lot of methane and a lot of ethane. And those are carbon-based materials. So organic chemistry can occur on Titan. And there are organic chemistry events and processes that are happening on Titan. The scientists think very similar to how they happened on Earth millions and millions of years ago before life evolved. So here's a picture of Titan compared to the other moons of Saturn. You can see this big yellow one is Titan. You can see it's the biggest moon of Saturn. There are 62 moons of Saturn, and Titan is the biggest one. And like I said, it's a water world. Here it is compared to some other planets. So you see Venus and Earth are roughly the same size. Titan is right here. A Titan day is 16 Earth days. A Titan year is 29 Earth years. And here's another interesting fact. The surface pressure is higher than on Earth when you're on Titan. The gravity is lower. The surface pressure and density are higher. You can see how huge Titan is compared to, it's actually bigger than Mercury. So diameter is 5,000 kilometers. Surface pressure is 1.5 of Earth's atmosphere on the surface. It's very dense. The atmospheric height, the distance up to the space when you're on Titan is huge. The atmosphere is very thick, which is why the pressure is so high. So high pressure and low gravity make it perfect for a drone or a helicopter. It makes it a lot easier to fly. It's very cold, 290 degrees below zero. So you can't go there. It's really, really cold. It's actually called cryogenic conditions. So it's a challenge from an engineering point of view. So I mentioned that Titan has a lot of methane, and that's a source of or an enabler of organic chemistry to occur. You need carbon. And amazingly, this carbon and the fact that Titan had carbon, or methane in particular, was discovered by Gerard Cooper, or Kuiper, sorry, in 1944 using a spectroscopic instrument. So pretty amazing. We've known that organic chemistry could happen on Titan for over 60 years. So here's a cutaway view of what Titan looks like inside. The atmosphere, of course, is the 1,000 or 1,200 kilometer atmosphere, mostly methane, ethane, no oxygen. There's no oxygen on Titan, or at least not significant amounts. After you get the outer shell is frozen methane, frozen ethane. Then you have liquid water here, which is the amazing part. There's actually an ocean inside of Titan. And the ocean is bigger than our ocean. Matter of fact, on Titan, there's several times the Earth's volume of water in that layer. And it's actually decouples the outer hard surface from the inner rocky surface, which is kind of unusual. So you see here, the blue part is water. then there's a high pressure ice beneath the water, and then there's a rocky, they call it hydrosilicate core, which is kind of rocky core with a lot of water mixed into it, water ice mixed into it. So a very strange cross section, but this is what's really super exciting to scientists, is seeing that much liquid water on a place other than Earth. There could be life in that water. Nobody knows. And this mission is not going to prove that there's life in the water, because we're not going to dig down through that core or through this shell. It's too difficult to get through that at this point. But there are pools of methane and ethane on the surface, like lakes of liquid methane and ethane. And since that's a organic chemistry there and it's liquid, it's possible that there's life in those lakes, those liquid lakes. This is a depiction of how much water is on Titan. These little blue dots here show it's the amount of water in the size of shown in a spherical dimension. So this, you can see Earth's sphere here. That's how much water is on Earth. You can see over on Titan, the sphere is bigger. That means there's several times as much water as the Earth has. And interestingly, Europa is another moon. It also has a lot of water. So how do we know anything about Titan, enough even to go there? Well, we've had previous missions. NASA has had some nice missions, and so has the European Space Agency. The most important one was Cassini. Cassini flew to Saturn between 2010 and stayed there for 7 years. And while it was orbiting Saturn, it actually came close to Titan and dropped a probe onto Titan. That's shown right here. Here's Cassini again. It was the Huygens probe. The Huygens probe had a parachute. It landed on Titan. And while it descended through the atmosphere to the Titan surface, it collected atmospheric data, wind velocities. It had a radar. It actually imaged the surface of Titan. So we know quite a lot about Titan, and that's very helpful for planning a mission to Titan. So here's a super interesting, I find it super interesting picture of a radar picture taken by Cassini. You see the ripples here on the surface on this left-hand picture? Those are sand dunes. So we know that on Titan, there are sand dunes, and they're pretty high too. So the Dragonfly vehicle has to fly over the sand dunes. Now, they're not sand like we know sand. They're methane sand and ethane sand. So it's a different element or different compound than our sand beaches, totally different, but similar in structure. And when the wind blows on Titan, and there is wind, it makes the sand dunes, just like the wind blowing on Earth makes and changes our sand dunes. There's some information about the atmosphere that Huygens and Cassini found. You can see over here in the picture, you see some water can erupt into the surface through what's called cryovolcanism. So there is frozen water, some on the surface. There are methane, ethane seas and lakes shown right here. There's clouds, there's rain. It's methane rain, kind of unusual rain. This CH4 is methane. So you can have methane venting. Anyhow, very interesting, strange a topology with dunes made out of methane. In other words, organic dunes. So this is the situation that scientists think was like Earth a long, long time ago. So what makes our world what makes this world habitable, and what chemical processes turned into life on Earth, and has life developed anywhere else in the solar system? Those are big questions that NASA wants to answer, and there might be life on Titan, and they want to go and look. So we already talked about Cassini and how it revealed the diverse atmosphere and surface of Titan. This is a depiction of the Dragonfly over on the right. Like I said before, it has 8 rotors. And since the gravity is 1/7 of Earth's gravity, it's easy to fly on Titan. And you may not know this, but since the density of the atmosphere is so high, that means that the rotors produce a lot of thrust, more than on Earth. So this vehicle can't fly on Earth. It's too heavy. It weighs 2,000 pounds on Earth. It doesn't generate enough thrust with the rotors to get off the ground. So it can only fly in a low gravity, high density environment, which is what Titan has. Now you can see the ground as it's depicted on this picture on the right. There are rocks, not like our rocks. They're solid methane ice rocks. And you can see in the background dunes. So you can imagine the vehicle has to be able to look at the surroundings, at the ground, and determine where the dunes are so it doesn't fly into a dune. And when it lands, these skids, if it hits a big rock, it could turn over and crash. So it's important to be able to clearly see the ground and be able to navigate based on what the cameras see. So keeping the camera picture clear is really important. So when I had mentioned before how it's going to go towards Titan full speed, many tens of thousands of miles an hour. When it gets to Titan, it's not going to orbit. It's not going to slow down with retro rockets. It's going to plunge directly into the atmosphere. And this picture on the left shows that. You can see here in the upper left of this picture on the left, the capsule is coming down through the atmosphere. It jettisons the rocket fuel portion. This is the portion that gives you the tiny fine adjustments in the trajectory as it's going towards Titan. By the way, it takes about 7 years to get to Titan. So there's a lot of opportunity for fine adjustments in the trajectory so that it hits Titan just at the right place. It releases that rocket portion, and now you just have the capsule. The drogue chute deploys. The drogue chute slows down the capsule, as well as, of course, aerodynamic friction. The capsule gets hot as it goes through the atmosphere while it's slowing down. Just like American or any capsule coming down into the Earth's atmosphere with astronauts in it, it gets hot, so there's a heat shield. After the drogue chute has slowed down the vehicle, a big parachute deploys, and the bottom of the capsule falls off, is dropped with explosive bolts. Those are exploded. The bottom lid comes out. The Dragonfly vehicle is inside. They drop the Dragonfly vehicle at the right altitude, shown here, and then the vehicle actually has to fly down to the surface by itself without any commands from Earth, because it takes hours for a radio signal to go from Titan to Earth and then back. I believe it's 1 hour each way. So since it takes so long for a radio signal to go one way and then back the other way, from Titan to Earth and from Earth back to Titan, no pilot on Earth can control the drone. It has to be autonomous. So all of the intelligence on how to recognize the terrain, how to fly, how to turn, how to go up in altitude, descend in altitude, all has to be in a computer on board the vehicle. So here's the landing ellipse. Again, it's important to land exactly where the scientists want to land, because they have plans on what they want to look at. So the vehicle is going to land in this ellipse, and then it's going to fly about 50 different missions when it's on the surface over a period of a few years. So quite a few flights. It's going to fly over the sand dunes. They just examine these interdune areas. There's this impact crater that scientists are very interested in, where, yeah, it says here organics are mixed with water. The scientists are very interested to fly to that crater, land in it, and do scientific experiments using the drill. So here's a picture of how the vehicle is going to do its routine flights. It's going to take off here. It's going to fly about 400 meters up. It's going to look at the ground, spot the dunes, record them, record where they are, spot other dunes, find potential landing sites that are interesting to scientists. And then as they went out, they looked at this landing area and found that this was a safe area to land. The rocks weren't too big. So then they're going to find a potential landing site over here, but come back and land on this site that's already been scouted. Again, they don't want to land on a big rock. So this is the sequence that they're going to go through about 50 times. It's called a leapfrog exploration strategy. So 16 Earth days is a Titan day. So the idea is to fly every 2 Titan days, so every 30 days, every 30 Earth days. And during the time that they're on the ground, they'd be recharging the batteries. So that's why they can't go much faster than 1 flight every month, because they have to recharge the batteries. So what's going on right now on the project? I work on this every day with these people you see in the picture on the right. We have done testing already in wind tunnels. You might not know this, but there's a wind tunnel in Langley, Virginia, that they can fill with the equivalent of Freon gas or refrigerant. And that gas is very heavy, is very similar to the density that's on Titan. So we actually test the rotors, those 8 rotors you saw, in that wind tunnel. It's called the Transonic Dynamic Tunnel, TDT, Transonic Dynamic Tunnel, NASA Langley in Virginia. An amazing national asset. They actually suck the air out of this tunnel, fill it with Freon, and then you can test your model in approximately the right atmospheric conditions for Titan. This right here is a vacuum temperature chamber at Johns Hopkins in Maryland. This is a test of the drill that's on that landing skid. Yeah, you can see the bit of the drill right here, and they're just showing that it's going to work, making metal chips here. This is another vacuum cryogenic chamber. You can see how huge it is. They can put virtually the entire vehicle in there when it's ready. It's not built yet, though. Oh yeah, here's a picture of the transonic dynamic tunnel test that was done, I think about a year ago. You can see that there's 2 rotors here, one right here and one behind it. There's a mount that goes into the side of the tunnel. And so this spins electrically. And we gathered very valuable aerodynamic data during that test. So we're going to be going in another test next year with 4 rotors. So that'll be an exciting event to the same facility in Langley, Virginia. Here's the team that worked on this. Here's about the size of the lander. This is the MMRTG, the thermoelectric generator. Here's the fuselage. Oh, I didn't mention this, but you might find this interesting. So outside of the vehicle, it's minus 297 degrees Fahrenheit. Inside, it's 32 degrees Fahrenheit. So inside the vehicle, it's relatively warm. Outside, it's cryogenic. It's super cold. So why do we do that? And how do you do that? How do you keep it warm inside? Well, the MMRTG, that thermoelectric generator, makes a lot of waste heat when it's making electricity. The waste heat is used to cool the inside of the vehicle. And the vehicle itself, the fuselage, is covered with insulating material. So it's like a huge Yeti cup, if you will. So inside is warm, outside is freezing cold. So why do we want to keep the equipment inside warm? Well, one engineering principle is that when you change the temperature of 2 different materials, they grow at different rates. So a computer, for example, a flight control computer that's inside is made up of copper and silicon and other materials. Well, if you make that cold, all those materials grow at different rates, and you can get cracking and breakage of parts because of that different growth rate. So if you take a regular PC like the one I'm talking on right now, and you cool it down to minus 100 degrees Fahrenheit, or surely minus 297, it'll stop working immediately because of the fact that the integrated circuits are made of metal and silicon. They'll crack and they'll be destroyed. So all that equipment has to stay warm inside so it stays healthy. And of course, that makes it a challenge to design all the parts that are outside. They all have to be of materials that are similar materials. They do flight testing on these models, so that's happening right now. And of course, it's a little bit not similar to what's on Titan, because this is 1G of gravity. Titan is 1/7. But it's really hard to flight test when you don't have access to a low gravity environment. And that is it from me. So it's like, yes, so we're 45 minutes in. I think we have Lori and Kate, if you agree, there's probably time for questions if there are any.
There's definitely time for questions. Bill, would you like to unshare?
Yes,
That would be great. Thank you.
thank you.
And everybody, you can change your view to gallery. If you change your view to gallery, you'll see the group. There we are. Here we are. So now, Bill, there are some questions in the chat. Would you like me to read them to you?
Yes, I'm still trying to unshare here. Hold
Oh,
on.
no, you did it.
Oh, I did it? Okay.
You did it. Yes, you
Well,
did it. Thank you.
spontaneous then.
Thank you.
Sure, please.
Okay, so we have a question from somebody, and then he says that you answered the question. But the question was, how do we know what's beneath Titan's surface? And then he says you answered it.
Yeah, I believe that when Huygens landed, it had a seismograph in it, and it actually was able to determine what's inside Titan approximately, because it's not perfect. A seismograph doesn't give you super precise information, for example, about the composition of what's inside a planet. It does give you some of that information, but it's not perfect. So I believe it was the information from Huygens, Cassini, and then computer simulations of the planet that are made to match those observations. And so there are some assumptions involved in those.
Okay. Then we have some questions about the water. So Hal says, if water is made up of oxygen and hydrogen, HO2, we know it is, how can it be water on Titan when Titan has no oxygen?
Now, that's a great question. I think maybe I should have said no oxygen in the atmosphere.
Okay.
Certainly there's oxygen as a compound in water, for sure. But there's no free oxygen in the atmosphere. And, I'm not a chemist. I should have made that disclaimer right at the beginning. I'm an engineer. So when I talk about chemistry, I'm an amateur for sure. So forgive me if I made any mistakes there, but I believe that any oxygen that would find its way to the surface would be immediately condensed and dropped onto the surface. So they know that there is cryovolcanism happening where the water is shooting into the atmosphere and then freezing immediately and dropping to the surface. So there's got to be trace amounts of oxygen in the atmosphere, but I believe it's just so small that it's insignificant.
Okay. We have a question from Martha. How or why is there a layer of liquid water between two layers of ice?
Yeah, another great question. So on the surface, it's too cold for water to exist. So the water can't be on the surface. And then what happens is beneath that hard crust surface, there's liquid water there. And then there's ice on the inside of that ocean. That's ice because it's under such high pressure.
Oh,
So it's under huge pressure. In fact, the ice that's underneath the ocean is a kind of ice that doesn't exist on Earth. It's a special form of water that has no analog on Earth. So it's almost like a different crystalline structure, I believe. Now you might ask, why is there liquid at all? How could you have a liquid billions of years after the solar system was formed? Didn't all the heat escape? If there was any heat inside of Titan, would it have not escaped? Well, the reason there's heat inside of Titan is because when it goes around Saturn, it gets there are tidal effects that essentially stress the entire planet, the entire moon. You can imagine squeezing it, then letting go, squeezing and letting go. That working on the due to gravitational effects of Saturn on Titan actually causes heat. And you can get an illustration of this yourself. If you take a paper clip, for example, and bend it repeatedly, do work on it, it gets warm. So whatever you stress repeatedly gets warm because you're putting energy into it. So gravitational tidal effects are causing heat that enables liquid water to persist.
great. Thank you. If there are more questions, please unmute yourself. And it's not a huge group, so you could just call out if you want. So we welcome you to unmute and question. Let's see, who do we have here? Pat?
I don't know. I don't have enough knowledge to form a question, but I am just amazed at what you all have been able to do. I think all of us are children of the space age. You know, we watched when Sputnik went across the horizon, and so I've always found this fascinating, but it is so complex.
It is, but you know, it's like any engineering scientific endeavor, you break it down into pieces, and it is amazing to me also. I have to admit. I mean, it's amazing to put an aircraft together out of millions of parts and have them all work. So it's amazing to me that we can take on something like this with some level of confidence. And, you know, it really is a team effort. I think maybe that's the key part here is no one individual has anywhere near all the knowledge. You need hundreds of people and a lot of dedication. And when you do that and you work in a cooperative way, you can do just about anything.
Which gives me hope that we can solve a lot of our problems if we could just get coordinated.
No, I agree. I agree. And another thing that I find very heartening is there's quite a few young people on the program. Well, everybody's young compared to me, pretty much. But it's inspiring to see newly graduated scientists and engineers that are so good. I tell you, the education in our universities, high school and university system is incredible.
Oh.
The knowledge of the scientists and engineers now coming out of universities is way better than when I graduated. So it's very inspiring to me to see that kind of that reality.
Mm-hmm.
And lots of women.
Absolutely. I mean, Zibby Turtle is one, and she's the leader of the entire project, $3 billion project, and she's a scientist.
Right.
Yeah.
3 billion. Wow. Wow.
It's very expensive. And, you know, I found it amazing that that's not even considered the biggest NASA projects, like the James Webb Telescope and the space station. Those are all hugely, they're way bigger than that. this is a relatively, it's not small, it's a medium-sized program.
I'll ask again.
Pat, well, hold on, let's wait. And Colin, we welcome you as our young guest. If you have a question or a comment, please feel free.
Yeah, I was actually typing one in the chat earlier, but I'll speak it out.
Hey,
I'm nice to meet everyone. I'm Colin. I'm Bill's cousin. So
Great to see you there, Colin. I'm glad you could join.
yeah, no doubt, it was very informative. But the question I came up with when you were going along there was, if Titan is approximately like Earth during those first few eons through the Hayden Archean, is NASA hoping to find Titan's version of Luca, which was the last universal common ancestor, aka the first cell to life on Earth, at least?
I'm sorry, could you, I didn't quite get the question.
I can't hear him.
Oh yeah, is that better?
Yeah.
Okay. I was curious if NASA is trying to find Titan's version of Luca, which was the last universal common ancestor. That was the first cell to be found, I guess, on Earth, allegedly. So if it was during the first Hayden Archean eons, I wanted to see if there was some similarities, if that's what they're aiming for.
I don't know, Colin. That's a good question. I guess, yeah, that would be a great question for the scientists. I would take a look at the NASA website. It's getting more and more detailed over time. And I do have perhaps some technical papers I could send you that kind of outline the details of the scientific missions. So yeah, good question, but I don't know the answer.
Pat, you had another question, Pat?
Well, I just put it in chat. When do you think this will be launched?
I believe it's in 3 years.
3 years.
And then
Okay.
it's going to take 7 years to get there.
That's a long time.
Yeah. Well, the vehicle doesn't actually exist at the moment. So we're just starting to build the parts, like the rotors, for example, are not even built yet. We're building the rotors for the wind tunnel, for the TDT, the transonic dynamic tunnel. But the vehicle itself has to be built. It has to be tested, has to be shipped to or trucked to Cape Canaveral, put on the top of a big rocket, and there's a lot to do in the next 3-4 years.
Yeah.
Yeah, so I hope to be working on this the whole time. So you had mentioned the early space race. I also was a kid during that time, and I always wanted to work on a space project. So this is my chance.
It is, definitely.
Hey, Bill,
Yeah.
I think this might be a good time to tell everybody that the Vertical Flight Society has a Vertical Flight Foundation. And this foundation funds scholarships for those young people that you're so impressed with. So if anybody listening to the program today is inspired to support education for engineers, Bill and I would be happy to take your money and get it to the Vertical Flight Foundation and support scholarships for engineers. A lot of people say, oh, those rich kids, they don't need any money for their education. Oh, yes, they do. Oh, yes, they do. It's a practical degree, and it's a wonderful way to help our world, because you know what? We might someday have to get off this planet and go someplace else. So anyway, I just thought I'd give a plug for the Vertical Flight Foundation,
Well, thanks.
funded through Vertical Flight Society.
Yeah, thanks. But I should say that a lot of the students that need money are not rich. They're humble people, but education, excellent as it is also expensive. So any help would be appreciated.
Yes.
So anyhow, I guess we're at the end of our time here.
Let's see, any last question? Nope. Okay, well,
Yes, thank you.
Thank you for
Bill,
sharing.
thank you
you're
so
welcome.
much.
Yeah,
Thank you, and again, welcome to you and Bernadette, our new members of Home Haven, and thank you so much for your contribution.
This
Well,
is great.
Thank you very
Thank
much.
you.
No, my pleasure. Thank
Good,
you
and
for the
we'll
great
see
question.
you. We'll see you around.
All
Okay.
right, take care. Bye-bye.
All right. Bye, everybody. Take care. Come to shredding on Saturday. Take care, everybody. Bye-bye.
Bye-bye.
Thank you so much.
Bye-bye.